Hello, everyone. My name is Jae Kim, and I am from Unist, South Korea. Today, I would like to present our work, TransPL, VQ code transition matrices for pseudo-labeling of time series unsupervised domain adaptation. This was the joint work with my professor, Sogi Lee. Generalization is one of the most important topics in modern deep learning problems. It is also very important in time series where you have to make your model generalized to different users with different characteristics like their age, height, weight, gender, and fitness levels. But naturally, users have different characteristics from one another. More formally, in deep learning, we say that there is a domain shift. Within the domain shift, we focus on the covariate shift problem where the relation between X and Y remains the same between the training and test, while the distribution of the X itself has shifted. So based on these setups, we look into the characteristics of time series that we should consider for deep learning modeling. Here is a visualization of the source and target users. This is an example of a person walking where the accelerometer sensors are plotted. The first notable characteristics is the temporal difference between the source and target users. The transition is faster for the source compared to the target, but the general patterns are rather very similar. As such, when we are adapting the source model to the target, we should consider these temporal differences. The second difference is a selective shift in channels. We observe that the degree of shifts differ by each channel. Here, as you can see, channel 2 and channel 1 have smaller discrepancy compared to channel 3. Consider the problem of unsupervised domain adaptation, in short, UDA. In UDA, training is conducted by having access to the labeled source domain and the unlabeled target training set. We validate the algorithm on the labeled source and test it on the target domain's test set. Likewise, we approach this adaptation problem by applying pseudo-labeling for the unlabeled target domain's training set. Here, we ask the followings for our research. We first ask, how can we model the temporality in the time series to construct pseudo-labels? We then ask, are there ways we can also incorporate the selective channel shifts that occur in time series into the pseudo-labeling process? Here, we provide an overview of our proposed work, TransPL. TransPL utilizes the source domain to make the pseudo-label for the unlabeled target domain. It basically has three steps. The first step is source training, where the objective is to train the VQVAE and the encoder with the labeled source domain. Source training will lead to suitable representations of time series instance by VQ codes. The second step is to construct two different types of course code transition matrices with the trained course codebooks, the class-wise transition matrices and the channel-wise transition matrices. The class-wise transition matrices is constructed from the source domain by collecting the transition patterns in a class-wise manner. As such, if we have two classes, we can construct two class transition matrices for the class 1 and class 2. The channel-wise transition matrices is constructed from the source and the target domain. This channel-wise transition matrices are used to assess the amount of shift between channel. Here, we note that we can still construct the channel-wise transition matrices for the target domain as we still know which channel the data is coming from. The last step is to construct a pseudo-label using the transition matrices. We will provide the details in later slides. The objective of source training is first, to pre-train the backbone encoder from the source domain, and two, we want to estimate the density of the source domain. However, directly estimating the density of a data distribution is infeasible due to the high dimensionality of the time series data. As such, here we discretize the continuous time series into our proposed coarse and fine VQ codes. The time series patches are first mapped to the coarse codes, where the residuals are mapped to our more fine-grained coarse codebooks. This intuition is borrowed from the conventional time series decomposition method, where the coarse code reflects the overall trends and fine codes maps the residual details of the patches. To train the codebook and the backbone encoder, we optimize the VQVAE loss terms as well as the cross-entropy terms. After completing the training of the source domain, we freeze the codebooks and the backbone model. We then utilize these models to obtain the coarse code representations of time series from both the source and target domain. As mentioned earlier, by aggregating these patterns in both class and channel-wise, we can construct two different types of transition matrices. So let me explain how the class and channel-wise transition matrices are used. For class-wise transition matrices generated from the source domain, we use them to calculate the likelihood of a coarse code sequence from the unlabeled target domain. Here, using the transition matrix, we can calculate the likelihood of this given BCA code sequence coming from a particular class. We note that while the temporal patterns may have changed from the source and the target, the overall transition patterns should remain the same. As such, using this likelihood, we can calculate the pseudo-label for each channels. Likewise, we can see that each channel of the target domain has now a pseudo-label. Next is the use of channel-wise transition matrices. What we do here is that we want to gauge the reliability of the pseudo-labels generated for each channel. As such, using the channel-wise transition matrices from both the source and target, we measure the optimal transport distance between the two. Lower distance between the two transition matrices indicate that the shift is small for that channel, and as such, we can place higher weights in that channel pseudo-label. We can use this weight in this part. So putting it all together, we first construct the pseudo-label for each channel using the class-wise transition matrices, and then measure the channel-wise alignment scores, and last, we aggregate these two in equation 1 to obtain the final pseudo-class label. Looking at this equation in more depth, we observe that this is simply Bayes' theory. We have the likelihood and the prior. So how can we set the prior? In most cases, we do not have the access to true label distribution. However, there are cases in motion time series where we roughly know the approximate time spent on each activity. This can be collected through self-surveys and questionnaires. More formally, this is called the weakly supervised UDA scenario. In our work, we can also incorporate this information through prior distribution. Now, I would like to provide our experimental results. We first compared our works to other UDA algorithms, and especially the pseudo-labeling methods. Here, we observe that our TransPL leads to strong domain adaptation performance compared to other UDA methods and pseudo-labeling methods. We also note that the pseudo-label of the target domain itself is well constructed based on the strong pseudo-label performance. We also note that incorporating the prior information, which is denoted as weakly supervised, of the label distribution leads to enhanced model performance. Moreover, we validate the use of transition matrices where we have incorporated our strategy with discriminative approaches such as 1D CNN, LSTM, and GRU. In addition, we compared our methods to CODATS, which is also an unsupervised domain adaptation method for weakly supervised setup. We show that while our methods leads to enhanced performance in all 4 datasets, CODATS may lead to degraded model performance when the prior is incorporated. Now, to wrap up our presentation, we have proposed a novel unsupervised domain adaptation algorithm known as TransPL. TransPL is a pseudo-label strategy which models the temporal transitions between the source and target users and also takes into account the selective shifts in channels via a view key code transition matrices. Thank you for listening to our presentation. If you have any questions, please feel free to let us know.